Good day and welcome back to our sixth and final installment on double integrals over general regions. In this video I wanted to focus in on two examples related to changing the order of integration, as this is a common difficulty that we encounter. Note in this first example we're not given a specific function that we're dealing with. We're simply asked to sketch this corresponding region of integration and then switch the order of integration. So let's begin by focusing in on this leftmost integral. And when I'm visualizing this corresponding region of integration, I'm working my way from the outside in. In terms of y values on the outside, we're varying from 0 to 2. And how I'm visualizing this is it's giving me what I'm going to think of as a horizontal strip of the xy plane where we will find our region. So our region lies between 0 and 2 in the y direction. Then what we need to think about is for a y value between 0 and 2, pick your favorite arbitrary value, we need to think, how do those corresponding x values vary? They vary from the lower curve, x equals minus the square root of 4 minus 1 y squared, and the upper curve, x equals positive the square root of 4 minus y squared. And hopefully at this point we've been practicing enough that we might recognize almost immediately what those curves represent. So note, x equals the positive square root of 4 minus y squared, represents the right half of a circle of radius 2 centered at the origin, but of course we only need that portion that's sitting in that range of y values from 0 to 2. So it's really kind of the upper right corner. So this would correspond to x equals the positive square root of 4 minus y squared, whereas x equals minus the square root of 4 minus y squared would correspond to the left half of that circle. So we're thinking for a y value between 0 and 2, the corresponding x values vary along these horizontal lines, going from the smaller green curve up to the larger blue curve. Now that we've sketched the region of integration, I am going to redraw it to the right and then use this picture to determine our new limits of integration when we switch that order around. So note, our region of integration is made up of the top half of a circle of radius 2 centered at the origin. So if we have x on the outside, we can note that our x values are varying from x equals minus 2 to positive 2. And then we would like to ask for any arbitrary x value we pick between minus 2 and 2, how do those corresponding y values vary? And note, they vary from this lower curve, y equals 0, up to this upper curve, which would be the top half of a circle of radius 2. So y equals the square root of 4 minus x squared. And for any value of x between minus 2 and 2, you are varying on these vertical line segments from y equals 0 up to the top half of that circle. So our limits of integration on the inside y integral would be 0 to the square root of 4 minus x squared, which completes the current example. But the real power of this technique of switching the order of integration becomes apparent in this next example. The idea being, if you wanted to evaluate this inside integral with respect to y, that would be difficult and time consuming. You'd have to somehow factor that denominator, maybe do a partial fraction decomposition. But in terms of x, 1 over y cubed plus 1 is a constant, so you could easily evaluate that integral. So let's go ahead and switch the order of integration. That is, we somehow want to write this as an integral of 1 over y cubed plus 1, but the order will now be dx dy. So the exact type of problem we worked through above, It's just now that once we switch the order of integration, we will also have an integral to evaluate. So kind of 2 for the price of 1. So looking at the integral that we're starting with, working our way from the outside in, x values vary from 0 to 4. So if we're thinking of our x values from 0 to 4, that's giving us now kind of a vertical strip of the xy plane where we can find our region. What we need to think about is if we pick any value x between 0 and 4, doesn't matter which one, how do those corresponding y values vary? And they're going to vary from the curve y equals the square root of x up to y equals 2. So I'm going to go ahead and sketch those in. Y equals square root x would look something along these lines. And note this point would be 4 comma 2 because the square root of 4 is 2, so that y equals 2 is the horizontal line. Now, for an x value between 0 and 4, the corresponding y values vary from the lower curve, y equals square root x, to the upper curve, y equals 2. So we're really thinking of our region as being made up of these vertical line segments. In order to switch the limits of integration, let me redraw this region of interest. So we have y equals the square root x and y equals 2. If we want y to be our outside variable of integration, we think what 2 numbers does y vary between? Y varies from 0 to 2. And that gives us our outside limits of integration. And then for a value of y between 0 and 2, we need to think, how do those corresponding x values vary? And they now vary along horizontal lines, going from the lower curve, x equals 0, to the upper curve, x equals something. And note, if y is the square root of x is equal to y squared. So the inside limits of integration will be from 0 to y squared. And note, I consider this to be the difficulty of the question, or at least the new part. Once we've switched around the order of integration, this becomes a much more reasonable integral for us to evaluate. So note, just to get one step written down, if we evaluate the inside integral with respect to x, 1 over y cubed plus 1 is a constant, and then we evaluate from 0 to y squared. So substitute in x equals y squared, put a minus sign, substitute in 0. And the remaining integral with respect to y is a very reasonable integral, and you can evaluate this using a common technique of integration. And just for practice, I'm going to leave those details to you, but I will note when you evaluate this, you should end up with 1/3 the natural log of 9. This completes our discussion of double integrals over general regions. As usual, there are plenty of good suggested problems for you all to practice. If you have questions, drop me an email, stop by virtual office hours. Stay tuned and take care.